Myself, K. Sirisha, working as assistant professor in MBR College of Engineering and Technology in mechanical department. Today we are discussing in third unit problems. So here the problem is given like that. A reversible power cycle is used to drive a reversible heat pump cycle. The power cycle takes in Q1 heat units at T1 and rejects Q2 and at T2. The heat pump abstracts Q4 from the sink at T4 and discharges Q3 at T3. Show that the ratio Q4 by Q1. So we have to show that here in the form. So first of all, what is the given data? So the matter we will convert in the form of the diagram. First of all, he will give a reversible power cycle is used to drive a reversible heat pump. So here he is used to drive the heat pump. Whenever the using heat pump or refrigerator, we want work done. So we will take work from other system and this work we will use to run the heat pump or refrigerator. So here it is a diagram. So first of all, we are using heat engine from the above matter. The reversible power cycle is used to drive a reversible heat pump cycle. The power cycle takes in Q1 heat at temperature T1 and rejects the heat Q2 at T2. So the heat pump abstracts Q4 from the sink at T4 and discharges Q3 at T3. So show that the ratio. So first of all, we will take the heat engine and it extracts heat Q1 from source at T1 and rejects heat at T2. So this is the heat engine. So whenever the temperature flows from higher temperature to lower temperature, we get the heat engine and this heat engine gives the work done. So from above. So the power cycle takes at Q1 at T1 and rejects Q2 at T2. So that is the meaning of heat engine. Okay. So whenever the temperature flows from higher temperature to lower temperature, we are having the heat engine and it gives the work done. And this work is given to the heat pump and it runs we get the heat. So how to get? So this is the diagram. So source sink Q1 Q2 T1 T2 and gives the work. So what is the work? Q1 minus the difference of Q1 minus Q2 gives work done and this work done is given to the heat pump. So whenever the work is given to the heat pump, the temperature flows from lower temperatures to higher temperature. Okay, so the temperature flows from T4 to T3. So at Q4, heat supply of Q4 and Q3. Okay, here what is a Q3? Q3 is nothing but what is the gear here? Entering. This is also entering is equal to this is leaving. Okay, actually this arrow is up, not down. Arrow is up. So Q3 is equal to W plus Q4. Actually, this arrow is up. So Q4 to Q3. Drawn. So up arrow. So Q3 is equal to W plus Q4. So what is W? W is nothing but Q1 minus Q2. So for a reversible power cycle, power cycle, actual efficiency is equal to output by input. Here in our heat engine, what is our output? W. What is our input? Heat supply. So in heat engine, Q1 is the heat supply and W is the output. So the efficiency is nothing but output by input. Output is W by input is Q1. So what is W? Q1 minus Q2 by Q1 heat supply. So actually according to the thermodynamic temperature scale, whenever the Q's are there, we just replace temperatures. So Q1 by Q2 is equal to T1 by T2. At the same thing here also, we just replace Q's with the temperature T1 according to the thermodynamic temperature scale. So thermal efficiency is T1 minus T2 by T1. Also for a reversible heat pump cycle. Actually here heat engine having the efficiency and heat pump get the coefficient of performance. So engine gets the efficiency and pump and refrigerator get the quotient of performance. So what is the quotient of performance? Actually, quotient of performance is nothing but desired effect to work done. Desired effect to work done. that is the COP. So whenever we will consider heat pump, our desired effect is T3. So whenever the higher temperature is there, in between the T3 and T4, higher temperature is T4. So whenever we are having the higher temperature, we get okay. So whenever get the COP, so whenever get the higher temperature in between T3 and T4, T3 is the higher temperature. So at that place we will get the heat coefficient, desired effect. So if you replace the heat pump with refrigeration, because of heat pump and refrigerator, both are getting the same processes, but the desired effects are different for heat pump and refrigerator. So here our heat pump desired effect getting at the T3 and Q3 at T3 at whenever get the replace heat pump is replaced with refrigerator, we will get desired effect in sink. Okay, here also for a reversible heat pump cycle, COP is given by what is our COP? Desired effect to Vogadon. What is our desired effect? Already I told the heat pump desired effect get Q3 at T3. So T3 by work done is Q1 minus Q2. Sorry, desired effect is Q3. Okay, desired effect is Q3, and here are getting the Q3 minus Q4. Here our Q3 minus Q4. So Q3 higher temperature minus lower temperature. So here the work done of heat pump is Q3 minus Q4. Okay, so just replace Q's with the T's. So T3 minus T4. So here this is multiplying equations 1, 2, 1, 3, 2, 4. What is 1? 1 is Q1 minus Q2 by Q1. Okay, here T1 minus T2 by T1. And next Q3 by Q3 minus Q4, T3 by T3 minus T4. So multiply equations with 1, 3. 1 is Q1 minus Q2 by Q1 into 3 is Q3 by Q3 minus Q4 is equal to 2 and 4. T1 minus T2 by T1 is into 3 by T3 minus T4. Okay, so here Q3 minus Q4 is W, and here Q1 minus Q2 is also W. And just observe here our heat engine our work done is difference of Q1 minus Q2. Here our heat pump our work done is difference of Q3 minus Q4. Okay, take separately. So Q3 minus Q4 is equal to Q3 minus Q4 is equal to Q1 minus Q2. So W. Just first of all we will consider LHS set. So this is LH set and this is RHS set. This is RHS set and this is LHS set. Okay, our LHS is Q1 minus Q2 by Q1 into Q3 by LHS is Q3 by actually Q3 by Q3 minus Q4, but we will replace Q3 minus Q4 is with the Q1 minus Q2. And finally we get LHS is Q3 by Q1. Okay, so how can we write Q3? Already we mentioned Q3 as in the above problem. Q3 we mentioned actually this is upside down. Q3 is equal to W plus Q4. Okay, just replace Q3 with W plus Q4 by Q1. What is W? Q1 minus Q2 plus Q4 by Q1. So Q1 minus Q2 by Q1 plus Q4 by Q1. So in Q1 minus Q2 by Q1, we just replace with temperatures T1 minus T2 by T1 plus Q4 by Q1. Okay, this is our LHS. This is our LHS. So our LHS is equal, what is our LHS? T1 minus T2 by T1 plus Q4 by Q1. So this is our LHS. This is our LHS is equal to this RHS. Okay, what is our LHS? T1 minus T2 by T1 plus Q4 by Q1 is equal to, this is our LHS and is equal to above mentioned is RHS. So this is our RHS. So LHS is equal to RHS. T1 minus T2 by T1 into T3 by T3 minus T4. This is LHS and this is RHS. We just modify the LHS and finally modified LHS is equal to RHS. So Q4 by Q1, T1 minus T2 by T1 into T3 by T3 minus T4. Okay, minus T1 minus T2 by T1. And just we calculated that just what we do here, what are we doing here? Just this term we will subtract here, and t1 minus t2 we will common t1 minus t2 by t1 and find t3 by t3 minus t4 minus 1. Okay, and just LCM that t3 minus t3 plus t4 by t3 minus t4, and finally we got q4 by q1 is equal to Q4 by Q1 is equal to T4 by T1 minus T2 by T1 by T3 minus T4. So this is our solution, final answer solution. And just look at what, there is no any confusion here. There is no confusion here. First of all, we will take heat engine. Actually, whenever the temperature flows from higher temperature to lower temperature, that is the heat engine, and it gives the work done. Okay, this work done is applied to the heat pump. So whenever the worker is given to the heat pump and temperature flows from lower temperature to higher temperature. Okay, here Q3 we will it is equal to W plus Q4 is equal to Q3, and this W is Q1 minus Q2, and separately heat pump of work done is Q3 minus Q4. So this is our entire diagram. So we will take this diagram and we will solve, and finally we got the Q1 by Q4 by Q1. And next problem we will see, we get once, determine the power required to run a refrigerator that refers 2000 kilojoule per minute of heat room from a cooled space at minus 273 degrees centigrade to the surrounding atmosphere at 300 degrees centigrade. The refrigerator operates on reverse coordinate cycle. First of all, our hint in the given problem is refrigerator. So I will told you in the previous class. So in a heat pump or refrigerator, definitely the temperature flows from lower temperature to higher temperature. Okay, so whenever the temperature flows from lower temperature to higher temperature, definitely we will supply some amount of energy. So when we supply some amount of energy to the system, at that heat flows from lower temperature to high temperature for only heat pump and refrigerator. Here our hint is refrigerator, so definitely heat flows from lower temperature to high temperature. First of all, heat transfer from cooled space 2000 kilojoule per minute, and temperature of cooled space T1 is equal to 273 Kelvin, and surrounding temperature T2 is equal to 300 Kelvin. First of all, this is our refrigerator. This is our here. This is our refrigerator. So sink is our cooled space, and our source is atmospheric pressure, atmospheric temperature. So lower temperature maintains 273. Higher temperature always source and sink. Source is mean higher temperature, and sink is lower temperature. So our hint is refrigerator. Definitely our arrow takes from lower temperature to high temperature. So when heat flows from lower temperature to higher temperature, definitely we will supply work done, and work done is nothing but power. We will supply some amount of power, then automatically it will flows from higher temperature to lower temperature. So here we will in our sink, it is heat observed, and it is a heat reference to the atmospheric temperature. So in our heat pump and refrigerator, definitely we will calculate the coefficient of performance. What is the coefficient of performance? Desired effect to work done, and work done is nothing but power. So desired effect in refrigerator, desired effect whenever it maintains the lower temperature, we will consider as this refrigeration effect or cooling effect or heat observed. In heat pump, whenever it is higher temperature, we will get the heat is supplied to the heat. So that is nothing but heat pump. But refrigerator is nothing but cooling. So cooling is nothing but cooled space. That is nothing but sink. So sink is our desired effect for refrigerator, and source is for heat pump. So our desired effect for refrigerator is sink. Sink is nothing but cooled space. That is Q absorbed the power down. Power. So Q observed is nothing. What is the temperature here? T1 by T2. So work done is nothing but work done is nothing but T2 minus T1. Higher temperature minus lower temperature. So T2 by T1. And just we will take T1 by T2 minus T1. Heat observed means 2000 kilojoule per minute by power is equal to 273 by 300 minus 273, and just calculate it, and power is equal to 197.802 kilojoule per minute, and power is equal to 197.82. So joule per minute, 1 minute is 60 seconds, so in the form of kilojoule per second. So power is equal to joule per second is nothing but watt. So finally we got the power in the form of kilowatt. Okay, and next, an engine operating on a Carnot cycle works within temperature limits of 600 Kelvin and 300 Kelvin. If the engine receives 2000 kilojoule of heat, evaluate the work done and thermal efficiency of the engine. So, whenever the engine given, definitely we will calculate the thermal efficiency. So, this is our given data. So, higher temperature is T1. First of all, we will consider the given data. So, first we will write it on the bar where what is the higher temperature and what is the lower temperature, what is the heat supplied. We will write first on considered data, then after we will make a diagram very easily. We will not get any confusion also. So the higher temperature T1 is equal to 600 Kelvin. Automatically our hint is engine. Engine is nothing but temperature flows from higher temperature to lower temperature. So whenever the consider the problem, so definitely we will take the hint. That hint is engine. Engine is nothing but heat temperature flows from high temperature to lower temperature. Okay, so here higher temperature, lower temperature, and heat supplied is 2000 kilojoule. And work, so we will calculate for work done, efficiency, and heat rejected from the engine. So for source, higher temperature, sink lower temperature, we will consider it is a engine, Carnot engine, and definitely our engine gives a work done. Okay, at the T1 source is nothing but heat supplied. At the sink, heat is taken from source, that is heat supplied, and rejected to the sink, it is a heat rejected. So already Q heat supplied is 2000 kilojoule. We don't know the value of heat rejected. We are going to calculate the value of heat rejected. Okay, so what is the efficiency of heat engine? Output by input. Here, output is work done, and input is heat supplied. QS. So the work done by heat supplied. So efficiency is nothing but output is work done and input is heat supplied. Actually, W is nothing but QS minus QR, but in the form of temperatures T1 minus T2. By heat supplied, it is also T2, T1, according to the thermodynamic temperature scale. Okay, thermal efficiency T1 minus T2 by T1. So what is the work done already given? So temperature is T1 minus T2 by T1. So efficiency we got 50%. So work done is nothing but efficiency is equal to work done by heat supplied. Already you know the efficiency is 0.5 is equal to work done by already heat supplied is given in the above data. So finally we got W is equal to zero point 0.5 into 2000, that is nearly that is 1000 kilojoule. So finally we got the results of work done by the engine is 1000 kilojoule, that is nothing but 1 megajoule, and thermal efficiency of the engine is 50%. What I want to tell you that students, so in heat engine we will consider temperature flows from higher temperature to lower temperature, and it gives a work. And we will calculate in heat engine, we are calculated thermal efficiency. Thermal efficiency is output by input. Output is work done and input to heat supplied. Okay, so it just q's is replaced with temperatures because of according to the thermodynamic temperature scales. Q1 by Q2 is equal to T1 by T2. Just Q's replaces with the temperatures according to the thermodynamic temperature scales. In here in heat pump or refrigerator, we will calculate the coefficient of performances, and heat pump we will get the desired effect from source, and refrigeration we will get the heating cooling effect or heat absorb whatever we will get in a sink. So desired effect we will get in a sink for refrigerator, for source in heat pump. Thank you, students.